All right, so vapor pressure changes depending on what liquids you have mixed together, or if you have a non-liquid mixed in there, which means that boiling point changes. Recall, a liquid will boil when its vapor pressure is equal to atmospheric pressure. So as you increase temperature, vapor pressure increases. Eventually, the two are equal and it's boiling. So if you mix something in there, you're going to change the boiling point because you're changing the vapor pressure, which means that the vapor pressure increase or decrease will change the boiling point, and that means that predicting the change of the boiling point can be fairly complicated. We tend to avoid that in these introductory classes just because it matters whether you're mixing a volatile or a non-volatile substance in with your liquid. You mix table salt in there, it's going to be straightforward. It's going to make that nice linear line as the vapor pressure decreases. But if you mix ethanol in there, then the boiling point is going to increase. The vapor pressure will increase, which means the boiling point will decrease. Okay, so it makes a difference, is what I'm saying, is that what you have going in there can change the boiling point in either direction. So we tend to focus on the freezing point because that's always going to go in the same direction, down. Hence why we call it freezing point depression. And it doesn't really matter what you have mixed in there. The freezing point is going to go down based upon molality or mole fraction, not based on what you've mixed it with. We tend to focus on mole fraction, not mole fraction. Sorry, excuse me. We use molality just because we do. It's just the way we do it. And this is what we use to talk about freezing point depression. So we discuss freezing point depression using this formula. Delta T equals KFM. It's one of the simpler formulas we use. Delta T means the change in freezing point. So it's the old freezing point minus the new freezing point. So it's always a positive number because freezing point always goes down. M just means molality. Okay? KF is the freezing point depression constant. Okay? It's a constant for each liquid. Okay? All it depends upon is the concentration for the solution. It doesn't really matter what the thing we're talking about is that's dissolved in the solution. Okay? And it has units of degrees Celsius per molal. Okay? So it just says, the freezing point will change by a certain amount based upon the concentration of the solution. So, for example, water has a freezing point depression constant of 1.86 degrees Celsius per molal. So what will be the new freezing point for a solution with a concentration or a molality of 0.20 molal? Well, delta T equals KFM. Delta T equals 1.86 degrees Celsius per molal times 0.20 molal. So the freezing point depression, the change in the freezing point is 0.372 degrees Celsius. Or, to put it another way, the old freezing point minus the new freezing point has a 0.372 degree difference. Or the new freezing point is 0 degrees Celsius minus 0.372 degrees Celsius, or negative 0.372 degrees. So the new freezing point is a little bit below the freezing point of water. It's not a huge change, but then it's not a huge concentration. But imagine, you have an icy sidewalk and you spread a whole lot of salt on it. Now your concentration is going to be huge because there's not much water there on the icy sidewalk, and you're just dumping a whole ton of salt on there. So you're going to have a really high molality. And then you're talking about salt. So it's going to be making multiple ions, for every unit of salt. So it's going to have an even higher molality. So you can get a freezing point depression of 10s or 20s degrees. So That's why we put salt down on roads. It keeps them from being icy until it gets really cold out because of freezing point depression. And in fact, we don't use table salt, sodium chloride. We use calcium chloride, which is CaCl2. So it produces 3 ions rather than 2, which means we're tripling the molality instead of doubling it. So yeah, that's one of the nice real effects that we have. Or we would if we lived somewhere up north instead of down here in South Carolina, where it doesn't get below freezing all that often, and when it does, we just put down sand. All right, let's talk about osmotic pressure. Okay, so osmotic pressure. Osmotic pressure refers to the tendency of liquids to move across semi-permeable membranes, like, for example, the membrane of the cell. That's why we're talking about this, because a lot of you are going into medicine stuff. If you, say, picture here, we have a U-bend, a tube in the shape of a U. It's got liquid on either side and a membrane in the middle. The liquid is pushing down, of course. So on each side, the liquid is pushing down with equal weight. And they're pushing on the membrane, I should say, as well, with that much weight. Now, if one side or the other, if one side is pure and the other side is impure, if it has some sort of salt dissolved in it, then they're not going to push on it with the same strength, and those fluid levels will be unequal. The pure side will push harder on the membrane than the impure side, so it's exerting more pressure. Now, is it a real pressure, this osmotic pressure? Sort of, yeah. The fluids are striking the membrane with some amount of force. They're able to pass through with some amount of frequency, and depending on the concentrations, the fluid will rise up to a certain level until the force of gravity is able to counteract the osmotic pressure coming in on the other side. So for, medical sort of relevance, this is why we use a 0.9% saline solution, because that 0.9% saline has, it is what's known as iso-osmotic. It's not quite, but it's very, very close to being iso-osmotic with blood. Iso-osmotic meaning that the osmotic pressure exerted by that 0.9% saline solution is almost equal to, it's as close as they can get with an easy measurement, to the osmotic pressure exerted by the fluid of the blood. So it doesn't cause your blood cells to shrivel up and die because of lack of fluid, and it doesn't cause them to swell up and burst and die because of too much fluid. So that is osmotic pressure. There's math associated with osmotic pressure. If you're really interested, I can show you, but I ain't going to do it here. Just be aware that osmotic pressure is a thing, and having stuff dissolved decreases the osmotic pressure, just like with vapor pressure. Okay? So when it comes to being able to push across a semi-permeable membrane, pure fluid exerts more pressure, just like with vapor pressure. So with that said, we are done with colligative properties, and we get to move on to our colloids. Okay, now, colloids. A solution is a homogeneous mixture that does not settle over time. A suspension is a heterogeneous mixture that does settle over time. Okay? So, like just a mud puddle, throwing sand into water, something like that would be a suspension. Okay, they'll float for a little while, but eventually they'll fall down to the bottom of the liquid. A colloid is somewhere in the middle. It is not a solution because it's not a homogeneous mixture, but it's not a suspension because it won't settle over time. So there are a lot of examples of colloids on tap. Smoke, fog, clouds, and mayonnaise. These are all examples of suspensions. Of colloids. Excuse me. And you might have noticed that they all have a similar property of being foggy, white. That is the Tyndall effect. See, colloids have large particles in them, and those particles tend to sort of clump together, and they are large enough to scatter light. So light will come in, and it'll hit those particles, and it'll bounce off randomly in all directions. That's why it looks white, is because it's all the light, right? It's not a preferential absorption of light, so there's no color to it. It's also hard to see because the light is being scattered. Any original image is going to sort of fade out, get washed away. And the reason I say that it is heterogeneous, okay, it's not homogeneous. Like I said, the particles tend to clump together. So a solution, the particles get spread out evenly throughout the solution, right? Throughout the solvent. But for a colloid, they're clumped together. So some will be on the outside of the clump, some will be on the inside of the clump. They're experiencing different environments. So that is why I call them heterogeneous. Mayonnaise is a colloid. It's a suspension of oil in water. Well, actually, of oil in vinegar. Those ancient peoples, well, I say ancient, but it was actually invented fairly recently, mayonnaise. Invented in Port Mahon in Spain, hence mayonnaise. What you do is you use oil and vinegar and an egg, and then you just beat them together, and the egg will emulsify. That's a nice fancy word. It'll emulsify the oil into the vinegar. And it appears white because it's scattering the light in all directions. Emulsify just means that the oil gets broken up into small droplets, and then those will sort of hang in place in the vinegar. Similarly, bile salts. For those of you interested in biology, bile salts are produced by the liver, and they are released into the small intestine. And those emulsify fats. They break the fat in our food down into just small droplets of fat so that they can be digested. Otherwise, we wouldn't be able to digest them. And if you have any sort of liver trouble, like say if you're an alcoholic and your liver is busy trying to break down, alcohol, it won't produce the bile salts, and so you'll have nasty poo. Because it'll just be full of fat that was not emulsified and therefore not digested. Let's see. Let's see. Soap. Soap is an emulsifying agent because what it'll do is it'll break up oil on your skin, on anything you want to wash, actually. It'll break up the oil into those tiny little droplets so that they can be carried away by the water that you're washing with. And soap gets all sudsy and white because it forms a suspension like that, or a colloid. And another one might be relevant for the ladies out there. There's that makeup that's supposed to, it changes to match the color of your skin, right? Well, not exactly. It's a colloid. It was always the color of your skin. It's just that while it was, thick and cream, it was a colloid, and it was scattering the light uniformly, so it looks white. But when it gets very, very thin, that's when you can finally see the color of the pigment that it always was. In any event, we're definitely not going to be doing any math with colloids. Just be aware that we're talking about somewhere between a solution and a suspension, a heterogeneous mixture that does not settle over time, that scatters light and thus appears to be white. And that'll do it for Chapter 11 and for Unit 1. So, good luck on the test, and I'll see you again when we start doing Chapter 12.